Imagine stepping into a glass capsule at sea level. No rumbling engines, no violent blast-off. Just a smooth, silent ride. Up. Past the clouds, past the atmosphere, into orbit 36,000 kilometers above Earth. It sounds like pure science fiction, but in Japan, engineers are quietly planning to make it real, and they have a deadline, 2050. The dream of the space elevator. The concept of the space elevator stretches back further than many realize. Originating in 1895, when visionary Russian scientist Konstantin Tsiolkovsky imagined a towering structure reaching from Earth's surface into the heavens. Inspired by the newly constructed Eiffel Tower, he envisioned a heavenly tower, so tall that it would touch the edge of space, a fixed structure allowing access to orbit without the need for rockets. Though his idea was more poetic than practical at the time, it planted the seed for what would later become one of the most ambitious engineering dreams in human history. Fast forward to the 1970s, and the concept took on a more refined and scientific form. Researchers reimagined the tower as a space elevator, a slender but incredibly strong cable anchored to Earth at the equator and extending beyond geostationary orbit. At the other end, a counterweight would keep the cable taut through centrifugal force. Instead of traditional rockets, the elevator would use robotic climbers to ascend and descend the cable, transporting cargo, satellites, and eventually humans, all powered by solar energy and electric motors. The benefits? Dramatically lower launch costs, safer transport, and near continuous access to space. For decades, however, this dream remained just out of reach, held back by one daunting, unsolved challenge: materials. No known substance could withstand the immense tension and stress such a cable would endure. Steel was far too weak, and even advanced alloys fell short. Until a material strong enough could be developed, the space elevator would remain a tantalizing vision, an idea suspended between science fiction and the distant future. Why Japan? Japan has a long-standing reputation for transforming bold, visionary ideas into concrete reality. It's a nation where engineering ambition meets disciplined execution, a blend that has led to some of the most impressive technological feats of the modern era. From the pioneering Shinkansen bullet train, which redefined high-speed rail travel in the 1960s, to the development of the Kibo module aboard the International Space Station, Japan has consistently pushed the boundaries of what's possible. So it's perhaps no surprise that Japan has become a leading player in the quest to build a space elevator. In 2012, the Obayashi Corporation, one of the country's largest construction firms, made global headlines by announcing an extraordinary goal: to construct a fully functional space elevator by the year 2050. Though the timeline is ambitious, the announcement was more than a publicity stunt. It marked the beginning of a serious, long-term effort to explore the scientific and engineering challenges involved. Since then, Obayashi has collaborated with universities, research institutions, and the Japan Aerospace Exploration Agency, or JAXA, to study the feasibility of the project. These efforts include testing carbon nanotube-based materials, simulating orbital dynamics, and exploring energy transmission methods for powering climbers. For Japan, the space elevator represents more than just a technological milestone or a symbol of national prestige. It's a strategic move aimed at securing a leading role in the rapidly emerging space economy, one where access to orbit is as routine as air travel, and where nations that lead in space infrastructure will shape the future. In Japan's eyes, the race begins with a cable. How it would work. Imagine a cable stretching 96,000 kilometers into space, more than twice the altitude of geostationary orbit. It begins on Earth, anchored to a floating launch platform in the Pacific Ocean, ideally located near the equator to take advantage of Earth's rotation. The cable extends upward, gradually thinning, until it reaches a massive counterweight in space. This counterweight could be a decommissioned spacecraft, a captured asteroid, or a purpose-built mass. Its job is simple but critical: to keep the entire system under tension by using centrifugal force, effectively pulling the cable taut as Earth spins. Now picture a series of robotic climbers, electrically powered vehicles designed to grip and ascend the cable. These climbers would haul cargo, satellites, or even human passengers upward at speeds reaching hundreds of kilometers per hour. A full trip from Earth's surface to geostationary orbit would take about 8 days. A slow but steady ascent compared to the brief intensity of rocket launches. Powering the climbers is one of the system's key engineering challenges. Some proposals involve ground-based laser arrays that beam energy directly to the climbers' photovoltaic receivers. Others envision solar panels mounted on the climbers themselves, collecting energy as they rise above the cloud layer into uninterrupted sunlight. This elevator wouldn't just serve as a transport line, it would be a launch pad for the future, a continuously operating, low-cost connection between Earth and space could redefine how we build satellites, space stations, and even interplanetary missions. Key takeaway number 1. Launching into space without rockets changes everything. Right now, launching anything into space is an expensive, high-risk operation. Even with recent advances in reusable rockets, like those from SpaceX and Blue Origin, the cost of sending just 1 kilogram of material into orbit ranges from $2,000 to $10,000. That includes fuel, launch infrastructure, safety protocols, and the rocket itself. A complex combustion-based process that's been the only way to reach space for over half a century. A space elevator could revolutionize all of that. By eliminating the need for rockets, it could reduce the cost of sending 1 kilogram into orbit to just $200, or even lower as the technology matures and scales. That's not just a price drop, it's a paradigm shift. With those economics, new possibilities open up almost overnight. Affordable space tourism becomes viable for more than just billionaires. The dream of everyday people visiting orbital hotels or lunar resorts could move from science fiction to travel brochure. Massive space-based solar power stations could finally be constructed. These would beam clean energy back to Earth 24/7, helping solve long-term climate and energy challenges. Bulk shipments of materials, including water, metals, and construction components would be sent to the Moon, Mars, or orbiting platforms for building habitats, research stations, or even entire colonies. And beyond the economics, it's a cleaner, safer, and more sustainable method. No explosions, no massive fuel burns, no multi-stage failures. Just electric climbers quietly riding a tether to the stars again and again. Japan's roadmap. Turning the vision of a space elevator into reality is no small feat, and Japan's Obayashi Corporation knows it. That's why their ambitious 2050 goal is structured as a series of carefully planned, incremental stages. Each phase builds on the last, steadily tackling the immense technical, logistical, and material challenges involved. The first stage spans the 2020s to 2030s, focusing on small-scale experimentation in orbit. During this period, the goal is to test core concepts in a low-risk environment. Satellite-based experiments are used to simulate the forces a real space elevator would endure. These tests focus on understanding how to maintain tension in a dynamic orbital environment, how climbers interact with the cable, and how to manage energy transfer in space. One such milestone came in 2018 when Japanese researchers successfully conducted a miniature space elevator test. In this experiment, 2 small CubeSats were deployed in low Earth orbit, connected by a thin cable. A tiny climber, just a few centimeters in size, traveled along the tether. While modest, the test marked the first-ever demonstration of an elevator-like movement in space. Looking ahead to the 2040s, the next step is to deploy a partial-length cable from a space-based platform toward Earth. This phase will test large-scale tension dynamics, climber operations over longer distances, and real-time control systems. Finally, by 2050, the full system 96,000-kilometer tether with a counterweight beyond geostationary orbit is planned for completion. At that point, Obayashi hopes to begin regular cargo runs between Earth and orbit, launching not with fire and noise, but with quiet electric precision. Key takeaway number 2. Costs drop from tens of thousands to hundreds per kilogram. The projected cost drop offered by a space elevator from $10,000 to as low as $200 per kilogram is more than just a technical improvement. It's a fundamental shift in how humanity can think about space. This isn't a minor efficiency upgrade. It's the difference between exclusivity and accessibility, between scarcity and scale. At today's prices, nearly every space mission must be ruthlessly optimized for weight. A single kilogram can cost more than a luxury vacation. That limitation shapes everything from how satellites are built to which experiments get funded. But with elevator-scale logistics, those constraints start to vanish. Instead of budgeting to launch a single space station, nations or corporations could build dozens, customized for research, tourism, or manufacturing. The idea of having a permanent crew in orbit not just on the ISS becomes economically feasible for universities, startups, and private investors. Instead of sending only tiny scientific payloads, we could launch entire modular habitats, greenhouses, or full-scale construction equipment to the Moon, Mars, or beyond. Colonization and long-term presence in space suddenly look achievable within a human lifetime. And perhaps most radically, instead of space being the domain of only the wealthiest governments, the door opens to private citizens. A future where individuals, students, or entrepreneurs can buy a ticket to low Earth orbit becomes imaginable, not centuries from now, but within decades. This kind of cost reduction doesn't just save money, it democratizes access to space, shifting it from an elite frontier into a new realm of human opportunity. The sky is no longer the limit, it's the starting point. The science and engineering. At the heart of the space elevator dream lies a materials science challenge so immense, it has defined the limits of the project from day one. For a cable to stretch tens of thousands of kilometers into space, under constant tension from gravity and centrifugal forces, it must possess truly extraordinary properties. Specifically, it needs a tensile strength of at least 130 gigapascals. That's more than 30 times stronger than the best high-grade steel we use today. The most promising candidate? Carbon nanotubes are cylindrical molecules made of carbon atoms arranged in a hexagonal lattice. These structures are incredibly light, thermally stable, and, importantly, mind-bendingly strong at the molecular level. In theory, they can easily meet the strength-to-weight ratio required for a space elevator. But there's a catch. While we've learned to produce short strands of carbon nanotubes in labs, scaling them up into uniform, continuous fibers thousands of kilometers long is a challenge that is yet to be solved. Consistency, alignment, and defect reduction are major hurdles in nanomaterials manufacturing. Beyond materials, the elevator must also contend with complex orbital mechanics. It will need precise vibration damping systems to counteract oscillations caused by wind, the Coriolis effect, and movement of the climbers themselves. And with Earth's orbit already crowded, advanced collision avoidance systems will be essential to protect the structure from space debris and errant satellites. In short, building the elevator isn't just about making a strong cable. It's about designing an integrated system where physics, engineering, and space operations all function together with precision. The science is hard, but the possibilities make it worth pursuing. Challenges and risks. As bold and transformative as the space elevator concept is, the path to making it real is anything but smooth. Several critical challenges and risks stand in the way, each one formidable on its own, and together forming a complex web of scientific, environmental, and geopolitical hurdles. First and foremost are material limits. No one has yet produced a continuous carbon nanotube or graphene-based cable long and strong enough for even a fraction of the required 96,000 kilometers. While lab-scale breakthroughs in nanomaterials are promising, The leap from centimeters to thousands of kilometers in defect-free material is unprecedented. Without a breakthrough in large-scale manufacturing and assembly, the cables simply can't be built. Then there's the issue of space debris. Low Earth orbit is already cluttered with fragments from old satellites, spent rocket stages, and even tools lost by astronauts. A stationary elevator cable extending through this crowded region would be a constant risk. That's why future designs include active collision avoidance systems, allowing the cable to shift slightly using tethers, thrusters, or electromagnetic forces to avoid impact. Closer to Earth, weather and geological threats come into play. The floating ocean platform, likely located near the equator in the Pacific, must be engineered to withstand typhoons, tsunamis, and earthquakes. These forces could exert massive stresses on the anchor point and lower section of the cable. Finally, there's the question of political control. Who owns, operates, and regulates a structure that connects Earth to orbit? Is it a national asset, an international utility, or a corporate project? With so much at stake, legal frameworks will need to evolve alongside the technology. These aren't deal breakers, but they are real, and they must be solved. Key takeaway number 3: opening the door to space tourism, solar power satellites, and interplanetary travel. Once a fully operational space elevator is in place, it promises to revolutionize not just how we reach orbit, but what we do once we get there. This isn't merely about transportation, it's about unlocking a vast new frontier of economic opportunity and human experience. Imagine tourists climbing quietly and comfortably inside sleek capsules, ascending the elevator tether to orbit. Instead of thunderous roar and intense G-forces of rocket launches, passengers would experience a smooth, scenic journey, floating in zero gravity while gazing back at Earth's shimmering blue curve. Space tourism would no longer be limited to the ultra-wealthy or a handful of astronauts. It could become a thriving industry accessible to many. Beyond tourism, the space elevator could enable the construction of gigantic solar power stations in orbit. These sprawling arrays would capture the sun's energy without atmospheric interference, then beam clean electricity back to Earth via microwaves or lasers. This could transform global energy markets, offering a constant, renewable power source to help tackle climate change and energy scarcity. The elevator would also dramatically change how we launch deep space missions. Instead of relying on expensive, heavy rockets for every stage, massive cargo loads, including spacecraft, habitats, and supplies, could be steadily lifted into orbit. From there, interplanetary missions to the Moon, Mars, or even farther destinations could be launched more frequently and at a fraction of today's cost. In short, the space elevator isn't just a method of transportation, it's a powerful economic engine, capable of driving humanity's expansion into space for generations to come. The 2050 Vision. By the year 2050, Japan's vision for the space elevator goes far beyond a single cable stretching from Earth to orbit. The dream is to establish a permanent, bustling space transport network that fundamentally reshapes humanity's relationship with space. In this future, cargo runs would become a weekly routine. Instead of rocket launches that require months of preparation and sky-high costs, vast quantities of materials, ranging from satellite components to construction supplies, would be steadily transported upward with electric climbers. This consistent flow of cargo would fuel the rapid expansion of orbital infrastructure and support lunar and Martian colonies. Passenger trips could occur monthly, opening the door for regular space tourism, scientific missions, and even business travel beyond Earth's atmosphere. The first few rides might be historic events, celebrated worldwide as humanity's bold leap into the next frontier. But over time, the millionth passenger's journey would feel as ordinary as boarding a Shinkansen bullet train in Tokyo. Efficient, comfortable, and utterly routine. The network wouldn't stop at Earth's orbit either. Space elevator hubs could serve as transfer points for shuttles bound for the Moon and Mars, creating a layered transportation system that connects Earth, orbit, and beyond. These inter-orbit hubs would allow spacecraft to refuel, resupply, and dock, enabling sustained human presence across the solar system. Japan's 2050 vision isn't just about building one elevator. It's about creating a spacefaring civilization, a future where space is no longer the realm of the few, but a frontier open to all humanity. A space elevator could transform humanity from a spacefaring species to a space-dwelling one. Japan's 2050 target isn't guaranteed. The material science gap is still huge, but the vision is alive, funded, and inching forward. Rockets took us to space. Elevators might let us stay there. Subscribe for more future tech deep dives and tell us in the comments, would you trust a cable to carry you into orbit? Stay blessed and stay curious.